Hello chemistry students. In this video I'm going to show you how to determine the number of valence electrons in an atom of an element. So up until now we've been talking about the nucleus of the atom and nuclear reactions. But what we're going to start studying very soon are chemical reactions. And chemical reactions occur because of interactions between the valence electrons of various atoms. And so it's important for you to understand how to determine how many valence electrons an atom actually has. So what are the valence electrons? Well, the valence electrons are the electrons that are found in the outermost energy level of an atom. So for instance, if we were going to draw an atom of carbon-14, our nucleus would have, our nucleus would have 6 protons, and we would have 8 neutrons, and then we would have 6 electrons. So, the electrons that are found here in the outermost ring that I'm highlighting in green, these 4 valence electrons, are what we have in a carbon atom. The thing is that to have to draw Bohr models for every single atom whenever you want to know how many electrons they have in the valence shell starts to get pretty tiresome. So here's a way to understand how many there are. So what we have to do is number the columns. So these are columns on your periodic table, and we need to number them. So we can do it like this. So our first column, which starts off with hydrogen at the top, this is column number 1. So I'm just going to write a oh wow, that's really thick. I'm just going to write a number 1 at the top. The second column, which starts off with beryllium at the top, is column number 2. Now you're probably like, well, we've already got a 1 and a 2 there, but those have plus signs in front of them. Those are charges. They mean something different, and we'll learn about that later. So for now, you can just ignore these numbers that we have above our columns. Now, what we're going to do is we're going to skip the next 10 columns. So these are going to be skipped because we're not going to use this method to figure out how many valence electrons these elements have. Instead, we're going to move on to the next column, which has boron at the top, and we're going to call this column number 3. The one that starts off with carbon is column 4. Nitrogen would be column 5, oxygen is column 6, fluorine is column 7, and then our noble gases, the one that starts with helium, is number 8. So what do these numbers mean? Well, if we go back to our column that starts with hydrogen, what this number 1 means that I wrote in pink is that all of these elements in the entire column that starts off with hydrogen, they all have 1 electron in their valence shell. All of the elements that are in column 2 have 2 electrons in their valence shell. All of the elements that are in column 6 have 6 electrons in their valence shell. So that's what all of this means. Now, there's one exception to the rule, and the exception to that rule is helium. So helium right here is our exception. It's in column 8, and so you would think, oh, it's got 8 electrons, except it doesn't. If you look at the atomic number for helium, you'll see that the atomic number is 2. It doesn't even have 8 electrons, period, let alone having 8 electrons in the outermost shell. So helium is an exception to this rule. It only has 2 electrons in the valence shell. So let's just draw a quick Bohr model for helium. So we have 2 protons for our helium, and let me make this a little bit thinner. 2 protons for helium, and because there are 2 protons, we know that there are also 2 electrons. So there's a Bohr model for helium. So why is helium grouped with all of these other atoms that have 8 electrons in their outermost shell? Well, the idea isn't necessarily about the number of electrons in the outermost shell. It's, is that shell full? Well, as you learned when you were drawing Bohr models, the very first energy level can hold a maximum of 2 electrons only. So by placing helium's only 2 electrons in that first energy level, we have filled its outermost shell. And so that's why helium fits with all of these other elements. So to show you a little bit more about what I mean, let me draw neon. Neon has 10 protons, and the first 2 will go in the first ring, and the final 8 will all go in the outermost shell. So because neon's outermost shell, the valence shell, has 8 electrons in it, it has a full valence shell, just like all of the other elements that are in this column. You may notice that the name of these elements, of this group of elements, are the noble gases. They're also called the inert gases sometimes, but noble gases are the more common name. And they're noble. They have a full valence shell, so they don't need to mix with other elements in order to gain a full shell. So they kind of stick with themselves. They're considered inert because they're largely non-reactive. You have to manipulate their environment to the extreme in order to get them to react with other elements. And the reason why is because they have a full valence shell. All right, let me erase this, and let's take a look at our problems down here. So for our element boron, we have a number 4 in parentheses there because it has 4 electrons total. Or I'm sorry, not boron, this is beryllium. Sorry, my mistake. It has 4 electrons total, so that's the atomic number. And if we come up to our periodic table and find element 4, there's beryllium right there. What number is above beryllium? The number 2. So we have 2 valence electrons for beryllium. Silicon is atomic number 14. So if we follow our atomic numbers until we find 14, we'll find silicon. And when we look up, we see that silicon is in group number 4. So it has 4 valence electrons. And if we look for the element with atomic number 36, here we are. This is krypton. And krypton is in that noble gases family, and it has 8 valence electrons. So that's how you do this worksheet, everyone. I'll post the key for you. Thank you very much for watching, and talk to you soon in class. Bye.